vertical line test. And then it asks you to determine the domain and range and write it in interval notation. The domain is which values? The x's, right? Any x that you can find that would map to a y value on the graph. And so which x values did you say work for this domain? What's the domain for the graph? What's the left boundary? -4. And what's the right boundary for the domain? Positive infinity. And does the 4 get a parenthesis or a bracket? Bracket, because it's an included value. What would have to change on the graph for it to be an excluded value or a parenthesis? An open circle, right? It'd have to have an open circle at the -4. The range is all the y values. That's from bottom to top. What's the lowest y value on that graph? 0. Does that get a parenthesis or a bracket? Bracket. And what's the highest y value? Positive infinity. Okay. So who got that? Whether it was in their head or on some paper. Symbols correct and everything? Okay. What we're talking about today is just domain. We're not doing range today. We're talking about how to find domains from equations. So we won't have any pictures at all, okay? It's real easy to do domain and range from a picture, but today we are just going to have stuff that looks like this. So if you look at the I will board, I will find the domain for y equals the square root of x minus 2 over 2x minus 5. And we're just doing domains. And so if we're just doing domains, that means we're only finding x values today. You'll be given a bunch of different equations, and we have to figure out what x values won't break the equations, right? It'll make them work. And so that's our goal for today. Here's this poor little baby for you to look at. Only, no range. And we're going to do it with equations, no pictures. And so we'll have to do some math, and we'll have to use our brain a little bit more than yesterday's lesson. To start this out kind of slowly, and you don't even have to write this down, I kind of want you just to look and think. Because we got to build up to that kind of equation, right? So let me give you an easy baby equation. Y equals x. This is called the identity function because no matter what you plug in for x, you get the same thing back for y. If you had a picture of this function, it would look like this. Well, so then we have to go through the 0. Hold on, let me just fix that. That's going to bother me. It has to go through. Okay, that's supposed to go through the 0. It's going through the 0. And that's a function. If you had a picture of it, what would you tell me for the domain? What x values would work for this function? All of them, right? Negative infinity to positive infinity. And if you were to write that in interval notation, it would look like this. Okay. Negative infinity, positive infinity. And that looks like y equals x. How do you think the domain would change at all, if instead of x, if I just had like 5x? What would the domain be for 5x? What x values would work for that function? What x's could I plug into 5x and do the math on it? All of them? All of them? Absolutely. All of them. So if I had 5x, the domain would still be negative infinity to positive infinity. If I added 3, what would the domain be? Is there any x's that wouldn't work there? No. Still all x's, right? All real numbers. Still negative infinity and positive infinity. If I squared this function, what do you think the domain would be? Is there any x values that break that function, that it wouldn't work? No, still all real numbers. Okay. What if I put this? Are there any x values that break that function? Yes. What x value breaks that? 4. 4. Because in the denominator, if you put 4 in, what will that give you on the bottom? If you plug in 4 for x? 0. How do we feel about 0 on the bottom? We don't like it. It's undefined, right? Cats and dogs living together, mass hysteria. You cannot divide by 0. So everything was going along swimmingly. It was all real numbers until I gave it a denominator with a variable in it. And then there's one number now that will break that function, and it happens to be 4. But every other number still works. So if you were to write that in interval notation, it would look like this. You'd have, and I like to always draw it on a number line first. If you remember when we worked with interval notation a few units ago, I would always recommend that to you. So originally it was all real numbers, which is this entire number line, but now we said, okay, you know what, 4 breaks it. So it's undefined at 4. 4 is an excluded value. But everything to the left still works, and everything to the right still works. And then if you were to write that in interval notation, you would just have to do this one and this piece. And do you remember how we joined those? What did we use? A U, right? And this is basically what we're doing today. We are taking functions. We are trying to figure out their domain. And keep in mind that whatever function you're given, we kind of don't care about the actual function. Like, we don't really care about what math is going on there. We only care about what x values won't break the function. We're just trying to find domains. And so the denominator that I just gave you is one specific situation that we're looking for. The other one is going to be square roots. And we'll talk about that here in a little bit too. So here's our first example, okay? We have this function, y equals x squared minus 5x plus 7. We want to determine the domain, meaning determine which x values won't break it, which will still work. And I want you to always start by assuming it's all real numbers, and then seeing if there's any special circumstances, okay? So we're going to just assume, we're going to start here. It's all the numbers on the number line. And then we'll look for special stuff, like, for example, is there a denominator anywhere that has an x in it, a variable? No. So there's no special situation where the bottom could ever equal 0, so we don't have to worry about that. Do you see a square root anywhere? The square root's the other thing we're talking about today. Do you see one? No. Do you see any situation where the function would break, that I couldn't put an x in because it wouldn't work? No, right? So if it won't break at all, you could put any x in any x you could imagine. You could plug it in and the function won't break. It will work. You will get a y value. That means the domain here is still all real numbers. Negative infinity to positive infinity. Because there's no special circumstances, okay? There's no denominators, there's no square roots. Here's this one. Okay, we have y equals 3 over x plus 2. We're going to start by just assuming all real numbers work, and then we're going to check for special circumstances, okay? This one has a special circumstance because there's a variable in the denominator. What number would make that denominator 0, which is very, very bad? Negative 2, right? And this one's easy to just do in your head. We know that x cannot equal negative 2, right? If it was a harder problem on the bottom, like let's say it was x squared plus 4x minus 4 or something like that. What I like to do is literally say, okay, this denominator cannot equal 0. I set it up as an equation and then I solve it. Sometimes in your homework you might have to factor first. Like this one is really, really easy. But you might have a quadratic down there that you have to factor and solve for, and that's, we've been practicing those skills. So I like to set it like literally not equal to 0 and solve it, and then that will give me the same thing in this case as we already did in our head. But that's a process that you can do for when the problem's harder. So it cannot equal -2, but it can equal everything else. So take a second and write that down in interval notation, because the picture is not the answer. Your interval notation is the answer. So take a second and write that. This lovely student has the correct answer. Who has that? Very good. Are there any questions about that? Okay, that was a nice appetizer problem. Okay, easing us into the lesson. Let's layer it up just a tiny little bit. Start by assuming all real numbers work, and then exclude values as you consider your special circumstances. Okay, so assuming all real numbers first, and then look at your function. Does this function have a denominator? Yes. Does the denominator have a variable in it? Yes. Okay. If it was just a number down there, like if it was just 7 on the bottom, we wouldn't care about that, because it will always be 7. But once you throw a variable in there, that's where you have to pay attention, because there are some values that plugged into x would make the bottom 0. You could probably do that in your head. What are they? What would make the bottom 0? 3 and -3, right? So x cannot equal 3 and -3. If you want a little math procedure to do that, because maybe sometimes you have one that you can't do in your head, what you would do is just sort of break that denominator off and say, okay, I don't want that equal to 0, so I'm just going to solve for x. Add 9 to both sides, square root, x cannot equal plus or minus 3. Right. And so if you can't do it, if you get something harder that you can't do in your head, just set it equal to 0 and solve for x. And those solutions are what will break your function. So it can be every number except, now we know, 3 and -3. So that's every number to the left of -3 will work. -3 breaks it. Between here works. Like if you tested out 0, it would work. 3 breaks it. And then everything past 3 will still work. There are 3 intervals there. So take a second, write your intervals, join them with some u's, and I'll give you a moment to do that. Nathan, do me a favor, please, and come write your answer. 2 u's. You didn't forget the middle interval, the -3 to 3. All right. Excellent job, class. Thank you, sir. Okay. So on your homework, for these kind of problems, you might have something in the denominator that looks like trinomial, like you might have to do swing method for it, okay? But still, you know what to do. You set it equal to 0, you swing method, you solve, and those are your excluded values, okay? Whatever makes it equal to 0 is bad. All right, so now we have this function. Do you see denominator in this one? No, so this one we got to talk about a whole different idea. We're not talking about what makes a denominator equal 0, because there is no denominator. Instead, we're going to talk about what kind of numbers we can take square roots of. In the real number system, what kind of numbers can we take a square root of? What kinds? Rational, but that's not the only kind, because we can, rational is good. Or maybe I should ask you this. What kind of numbers can't we take a square root of in the real number system? Negatives, right? Can't take a square root of a negative. What we're talking about right now is functions in the real number system, the coordinate plane. There's no i's here, okay? So we won't be taking square roots of negatives because we wouldn't be able to graph it. This is real number x's, real number y's. And so in this lesson, we'll only be able to take a square root of positive numbers. Now that's fine for me to say that in words, right? And you're like, okay, yes, Ms. F, positive numbers, I got it, positive. They have to be positive to take a square root. But that's not really mathy. Like, I need something with symbols that I can solve and do algebra. Here's how you translate the word positive into symbols. Any number that's positive, so here's my number, has to be what relation to 0? Can't be equal to 0, right? To be positive, has to be what? Bigger than 0, right? Aren't all positive numbers bigger than 0? Right? And so this thing that's under the radical, not including the radical, but the radicands, that expression or whatever the value of that thing is under there has to be positive. Which means this. That expression, that 2x plus 3, in order to be positive means it needs to be greater than 0. How do you feel about that? It's true, right? It's true. But to take a square root, it's not enough to just say it's only positive numbers. It can also actually be 0 too, as well. Because the square root of 0 is 0. So I don't know what the value is under the radical. I know it's 2x plus 3. And remember, we're trying to find domain, the domain that works for the function. I'm trying to find all the x's that I can plug in here and not break this. It breaks if that yellow stuff is negative. It doesn't break if the yellow stuff is greater than or equal to 0. That means it's positive. Now, I didn't do anything with that square root. I didn't remove it. I just simply took that stuff out and I'm talking about it, 2x plus 3. And so then if I actually solve this inequality for the x, I subtract 3 to both sides. (2x greater than or equal to -3), divide by 2, x greater than or equal to -3 has. That is a representation of all the x's that will work under that radical. Here's what it looks like on a number line. Here's -3 halves. Here's all the x's that are bigger than or equal to that. Because there's lots of numbers that will work. For example, 0 is right here. I'm just going to test this out. If you plug 0 in for x, what do you get under the radical? 0 plus 3 which is 3. Is that a positive number? Can I take the square root of 3? Absolutely. But if you tested something to the left of here, like let's say you tested negative 4, if you put negative 4 in there for x, you would get the square root of negative 8 plus 3, which is negative 5. That breaks the function, okay? And so that's why I just popped that radicand out, didn't actually do anything with the square root, and I said whatever is under there has to be greater than or equal to 0 in order to make the function work, because we're just finding x values that make it work. And these are all those. And then you just write it in interval notation. Okay. So any x in that interval is good to go. I have had a few people ask me today, but Miss F, what did you do with the square root? What did I do with it? Say nothing. That's right, I did nothing with that square root. I just took out that 2x plus 3 and I said, whatever's under there has to be bigger than 0, or it could be equal to, it has to be positive. And so then I do the math on it, and it gives me this range of values, okay? So we're going to talk about this last problem. This is not on your notes. This is from your homework. I want you to think about this for a second. I have some questions up here to help guide you. You're just going to find the domain for the function. We have the square root of x minus 2 on top over 2x minus 5. There's two things going on here. You have to deal with them separately and then put them on a number line and see how they play together. What is your concern about this first thing, the denominator, the 2x minus 5? There's a variable there. And we never want an x value that's going to make the bottom equal what? 0. So we don't want that. We don't want that to equal 0. So if we're looking at this thing first, we say, okay, we don't want this thing to equal 0. That's bad. And then the top with the square root, the radical, we want whatever's under here to be what kind of a number? Positive. But in math symbols, how do we write positive? It's in what relationship to 0, by the way? It's greater than. So we're not going to put is positive, because that's not going to do us good for math. We're going to say must be greater than 0, can also be equal to 0, and still take a square root. It's the stuff that's underneath the radical, not the actual radical part. So take a few seconds and sort of try to figure out this problem. So we start by saying maybe all real numbers work, and we're trying to find the ones that break it so we can exclude them. Like, for example, if I put, this is just something to show you. Tell me why x equals negative 2 wouldn't work for this function, for example. Where does it make the function break, Matthew? It would give me a negative, right, under the radical. So like that's an example of a number that cannot be in the domain because it will make the function break. So instead of guessing and checking every single number on the number line, which would be exhausting, we're going to use algebra for each piece to figure it out for us. And that algebra is two different things. For the denominator, it's this can never equal 0. Whatever is here can't equal 0. So I kind of set up a little mini equation that looks just like that. I say, all right, that cannot equal 0. I'm just going to solve that for x. I add 5 to both sides, and then I divide by 2. And I know that x cannot be 5/2, because if it was, and I plugged it in here, I get 0 in the bottom, and that's bad. So I can start, so the first thing I need to exclude from all the real numbers is 5 halves. So that's the first thing that I know is not going to work. And so once you've taken care of the bottom, you just kind of not think about it for a second. And you can go to the top. Now you have to figure out what makes that radical negative, because that would break it. And I saw a lot of people putting that x has to be greater than 0. Well, not necessarily. X could be 1. 1 is, and I know where you're going with that. You're feeling like it has to be positive under the radical. So x has to, she said, greater than 0. So x has to be greater than 0. But 1 is greater than 0. And if I put 1 in here, what do I get? 1 minus 2 is negative 1. And in the coordinate plane, the real number system, I can't take square root of negative 1. It fails. So it's not enough to say that x has to be greater than 0. What's going on is this. Whatever is under the radical has to be greater than 0. That entire expression. And so that's where we begin. We take that radicand, that's called the radicand, we pop it out. We look at it by itself for a second, and we say, this thing, not just the x, or not just the negative 2, but that entire expression has to be greater than 0 in order to be positive. It could also equal 0, because it's okay to take square root of 0. It's just 0. And then we get this, and we solve that. And we get, okay, x has to be greater than or equal to 2 to make sure that what's under the radical is positive every time. So we have to graph this now on our number line and see how it plays with the 5 halves. And my question for you is this. What side of 5 halves does 2 go on? The left side or the right side? The left side, right? So people haven't been putting 2 on the right all day long. But what is the value of 5 halves? 2.5, right? So 2 goes over here. If you put 2 on the right of 5 halves, it's okay. I mean, it's not correct, but don't feel too badly because it's been happening all day long. But you just have to slow down and think for a second about what you're doing. So we already have graphed this thing. We've already taken care of that. Now we need to do this. We have to incorporate that x is greater than or equal to 2. So I need everything to the right of 2. It can also equal 2. So I need a bracket. And everything to the right of 2 except 5 halves, because we already said that can't work. But everything else on the right does work. And so there's our graph, and now we only need to put it in interval notation. And that's so easy to do once you have your picture here. It's bracket 2 to 5 halves, parenthesis, because it's excluded, union, and then it picks up at 5 halves again and goes off into infinity. It goes off into la la land. Okay. Was anybody able to get that right from the start? Yeah? Okay, good. Who just made some tiny mistake, but now you're good? Who put the 2 to the right of the 5 halves? Messes up your interval notation, right? Gives you something completely different. All right, let me get you your homework.